In a prior video, we have demonstrated how to derive and solve the Schrodinger equation for the particle in a 1D box. In this video, we actually try to attempt to understand what those solutions mean. Right, so solving the Schrodinger equation for the particle in a 1D box model, which is what you have right here, we find that there's two solutions and they always come in pairs. The first one is a wave function, which has a value as follows. Okay, and the second one is the energy, which has these values. Here the parameters are, well, L is a quantum number, which goes from 1 all the way to infinity, but it has to be an integer quantum number, and this is very important. And then we have that M will be the mass of the particle, capital L would be the length of the box, and so forth. H is Planck's constant, and then you have pi. All right, so the way that we're going to explain this is by analogy to a microscopic particle. Okay, so the important thing to understand here is why is this any different from what we know from regular microscopic particles? Well, the first thing that you have right here is that the energy is quantized. Okay, so the energy cannot have arbitrary values. It actually is quantized. Here's why this is very different from a microscopic particle. If you have, for example, again, an astronaut traveling in the box left to right, okay, you can assume that that the velocity with which this astronaut is bouncing off the walls can have any value, right? If the energy has some value, then the velocity might be 5 miles per hour. But if you increase the energy a little, then the velocity will be 5.1 miles per hour. Well, that is actually not the case for the particle in a 1D box model. It turns out that the energy can only have very discrete values. Okay, if we now actually try to understand that using an energy scale in this box, where if you're right here, that will be low energy, and if you're right here, you'll have a higher energy. In the quantum world, you actually have that the energy is either that, which will correspond to what happens when you plug 1 here in N, or this, which is what happens when you plug 2 in N, or this, which is what will happen when you plug 3 in N, and so forth. Okay, the energy increases quadratically. But again, you can either have that energy, that energy, that energy, or the energies above. You can never have energies in between. And again, this is something that doesn't happen in the microscopic world. Okay, so that's the first difference, the quantization of energy. The second is that in the quantum model, the energy will never be zero. Okay, so even if you're at 0 Kelvin, no temperature, the first solution is not N0. The first solution is N is equal to 1, which means that your energy is actually never going to be 0, even if you're at the absolute 0 of temperature, 0 Kelvin. Okay? This is to satisfy the Schrodinger principle, which means that you cannot have full precision in what the velocity, the energy of that particle can be. Okay, so again, the energy of the particle can never be 0. At the 0 Kelvin, when you're in the ground state, N is equal to 1, okay, you will have a non-zero value of energy. This is in sharp contrast with what happens with a microscopic particle, where you can say that, well, that astronaut that is bouncing off the walls of the space station, right, the velocity can be 0, and the energy will be 0, the kinetic energy. Okay, and that doesn't happen in the quantum world when the length becomes very, very small, and then the mass is also very small. Okay, so that's what has to happen for a quantum particle. Okay, so those are two differences: energy quantization, and the energy is never 0 for the quantum world. Okay, there are other differences that we're going to explore right now, and that is the difference in the probability of the particle being anywhere on the box. Okay, so in the classical world, in the macroscopic world, when you think about a particle bouncing off the walls in this 1D box, you will see that the probability is exactly identical everywhere in the box, right? So your probability to be, say, if we divide here the box into parts, okay, you will say that the probability of the particle being on the right-hand side, the left-hand side of the box, and right-hand side of the box will be identical. But then you will say that if the particle is in the left fourth of the box, that probability is going to be identical to the second fourth, third fourth, and fourth fourth. There's no difference in the probability anywhere in the box. Okay? Now that is actually going to be different in the quantum world. we know that in the quantum world, the probability is related to the wave function. Okay, so the first thing that we're actually going to do is draw here the wave functions for some of these states. Okay, so this is 0, x to L, and then if we draw n is equal to 1, okay, the way that this wave function looks like, right? So you plug here n is equal to 1 right there, and then put this as a function of x from 0 to L. What you will find is that n is equal to 1 looks like this. It's a sine function in which you go to 0 twice, and that's right at the edges of the box. Okay, we can do the same thing now for n is equal to 2. Okay, 0 x L for n is equal to 2, and the way that this would look like is something like this. Okay, where you have that the wave function goes to 0 3 times, and let me actually draw this a little better. Okay, this should go through 0 right at the middle of the box, right there. Okay, so it goes to 0 3 here, there, and there. That's what happens when you put in n is equal to 2 right here, and then represent this. N is equal to 3, we can also represent that right here. Okay, it will be something like this. Okay, that is n is equal to 3, and again these are just the wave functions as a function of the position on the box. And then you can see how this will work for n is equal to 4, n is equal to 5, and so forth. Okay, yes, we're going to represent all of that here. Okay, but we're actually going to offset the wave functions in terms of their energy. Okay, so the energy of the n is equal to 1 state will be here, the energy of the n is equal to 2 state will be up here, n is equal to 3 will be up there. Okay, so this wave function is going to look like this for n is equal to 1, it's going to look like this for n is equal to 2, and it's going to look like this for n is equal to 3, and so forth. Okay, now, that is the wave function, but what we know is that there is a wave function squared that is related to the probability. So the question is, well, how do these wave functions look when you actually square them? All right, so we're going to draw them right here, squared. I'm going to erase this to just make more room. All right, so again, according to the Born interpretation of the wave function, it's the squared of the wave function that actually tells you about the probability of the particle. Right, so now if I square this for n is equal to 1, it will be n is equal to 1, I get a wave function squared that looks like this. Okay, if I square then n is equal to 2, and I put it a little higher, okay, it will look like this. Alright, well the difference is that, well, the wave function here was positive, the wave function here was negative, but they had exactly the same value. So then when you square them, both of them are going to be positive, both lobes will be positive, and then you would get something like this. Then for n is equal to 3, you'll have something like this. 1, 2, 3, and you can see how this will change as you go to n is equal to 4, n is equal to 5, and n is equal to 6. Right, so this is dramatically different from what happens with a microscopic particle. Right, we have said that for a microscopic particle, the probability is identical anywhere you're in the box. That's not the case for a quantum particle. If this is a quantum particle, what will happen is that if you're in the first state, okay, the maximum probability will be at the center of the box, which again makes no sense compared to a microscopic particle. All right, and then the probability is the same on the left and the right for each one of the states. Okay, but again, notice that in n is equal to 2, the probability is maximum at the center of the particle. However, if you add some energy to this particle so that it can reach the second energy state, okay, it turns out that the probability will be maximum right here, which is 1/4 of the box, and right here will be 3/4 of the box. It's maximum there, but it will be 0 exactly at the middle of the box. Okay, so what that means is that this particle is moving inside this box left to right, right to left, okay, but if it's in the n is equal to 2 state, it has a 0 probability to ever be found right at the middle of the box. And again, this is something that only happens in the quantum mechanical particles. It makes no sense when you try to attribute this to a macroscopic object. Okay, this is what we call a node, which is a point in space where the wave function becomes 0, okay, in between the limits of the wave function, the extrema of the wave function. Okay. okay, that is a node, and it plays a major role in a lot of chemistry. Okay, for example, orbitals of electrons in molecules and in atoms, they also exhibit these nodes. Okay. Now, when you go to n is equal to 3, notice that you will have 2 nodes. If you go to n is equal to 4, you will have 3 nodes. N is equal to 5, you will have 4 nodes, and so forth. The number of nodes increases with the state. Okay, so this is going to have a little bit of an explanation for how the solutions to the Schrodinger equation are quite different from what you expect for a microscopic particle. A microscopic particle, the energies can have any arbitrary number, you're not restrained, and the energy can be zero. In the quantum world, the energies have well-defined values, and the energy can never be zero. Okay? And also the probability distributions are very, very different. Okay? In the case of a macroscopic particle, the probability distribution is identical anywhere in the case, in the box. In the quantum world, the probability is not identical anywhere in the box, and it depends on what state you are. In some states, you actually have that the particle is most likely to be found at the center of the box. In some other states, it happens that the probability at the center of the box is actually zero. Okay, and again, this really puts into context the comparison between macroscopic and microscopic particles. Okay. Now, in the next video, we're going to see how this gets applied to an actual molecule, where we can test whether all of this behavior that we're actually finding from the quantum solution to the 1D particle in a box, okay, how that actually comes to be, and whether we can test whether all of these solutions are actually correct.